All right, so this video will have an example of determining, using our stress transformation equations to determine the state of stress on an inclined plane that's cut through our typical XY coordinate look at our stress element. Again, the idea here is the XY stresses that will determine from some combined loading is just kind of a convenient choice of coordinates, but it doesn't necessarily mean that that's the critical stress is important for the strength of a material. So our state of stress given in the XY coordinates is given here. We have, well, let's just take this as the picture. I should say this is problem number 1232 from the book. But from this, we should be able to write out all our givens that we'll need to apply our stress transformation equations. And those quantities that, there's four quantities that we need to glean from here to use in our stress transformation equations. Two are two normal stresses, a shear stress, just a single shear stress for plane stress, and the angle of rotation. Okay, so let's look at what those are. We see our normal stress in the x direction is a negative 2,885 psi, and this is in compression just because it's drawn inward, so that's a negative quantity. Our normal stress in the y direction is a positive 1,305 psi, and this is in tension, drawn outward normal. And our shear stress is a negative 2115 psi, and the reason it's negative is you can look at any face and go to our sign convention here, and any face you look at will return a negative result. So if we're in the on the positive y face, so up top, these y. Oh, actually, I'm sorry. This first one I have is the negative x face. Well, you can find all four different combinations here, so I'll just talk through them, and you can find them. But if we go to the positive x face, so that means that the face where if you drew the outward normal direction would be in the positive of that coordinate. So in the positive x face, our shear stress is in the negative y direction. So the combination of the positive and the negative give us a negative quantity. If we go to the positive y face, this is in the negative x direction. If we go to the negative y face, this is now negative x face is now in the positive y direction. And if we go to the negative y face, this is now in the positive x direction. So all four sides have one positive, one negative. And again, the configuration of this shear stress, these arrows, two sets of two pointing together is a result of equilibrium and must be true for our plane state of stress. All right, so those are three of the variables that go into our stress transformation equations. The other is theta, the angle of rotation. And in this one, it's a little bit tricky. We're given that we want to know the state of stress on, or the stresses acting on this inclined plane cut at a 50-degree angle this way. So it might look like you should just be able to plug in 50 degrees. But no, this is the angle that goes from the y face to the n face. It's not the angle that, in between the x and the n direction. So if you look at it like this, what we're interested in here is the actual state of stress on this face. So n acts outward normal to that face. We know that it's 50 degrees from x to the t, right? So the t, the transverse direction from this, so the tangent coordinate of this plane, the inclined plane, that is rotated 50 degrees, right? But we define our theta to be the rotation from x to n. And so together these two angles make up 90 degrees, and we see that actually our n is in a negative theta direction. It's a negative rotation. It's a clockwise rotation, which based on how we have signs for thetas and angles, that's a negative rotation. So we need to take 90 degrees minus the 50 degrees, and then it's a negative rotation here. It's a clockwise rotation which has a negative angle. All right, so our theta then is negative 40 degrees. Once we have that, we're ready to go to our stress transformation equations. The first one is our normal stress on that inclined plane. The normal stress is, the equation is written here. Again, the known quantities are sigma x, sigma y, tau xy, and theta. And once we have all those, which we've drawn out here, we can do everything. Plug them all in, calculate it, 929 psi. It's a positive quantity, meaning that there's a tension stress acting on the inclined plane, which we'll draw as an outward normal on our wedge element. If we go to our shear stress acting on the inclined plane, this is our stress transformation equation. Again, we see a sigma x, a sigma y, tau xy, and theta, and nothing else. Those are our four quantities. We determine them and listed them out up here. If we plug them in, we get negative 2430 psi. And so here's a good result, or an interesting result, that by a rotation, we got an even stronger shear stress than is originally acting in the xy plane. And so maybe you're really picky about your shear stress. This, the strength of the material is really sensitive to shear stress, and you're approaching it here. But with your analysis, you find that 2115 might be good enough, but you can't go above 2200 psi. Well, along some rotation, we're going to hit that. It's 2430. That's over 2200. So that's just an example. So we do get a negative quantity here for shear stress, which means that when we go to our positive end face, this will be acting in that negative t direction. And that's how we draw this element. First, we'll start over here. This is the x compressive stress. This is the y tension stress. Those are our normal stresses. In green, on the x and y faces, we have the tau xy, which is 2115, and it's negative, but the negative comes from the directions that they're drawn. Here's our 50-degree angle. Again, that was originally drawn down here, but that's the same angle as up here. And we have our outward normal, so a tension stress that we determined right here, 929 on the end face. And the shear stress acting on that face has a magnitude of 2430 psi. And now here's where we see this is on the positive end face. This is in the negative t direction, so counter to the t direction. Okay, so that wraps up the example problem for our first go at the stress transformation equations. And from here, we're now prepared to look at the rotation about which we'll get maximum quantities for both of these stresses.